This video is sponsored by RadiaCode. Imagine a metal that is so unusual you could almost mistake it for a piece of cheese. It's not gold, silver, or anything you've likely held in your hand. This metal is so soft that you could actually cut it with a butter knife. Bend it and it even makes a faint crying sound. And here's the twist. Without it, the touchscreen on your phone or tablet simply wouldn't work. This quiet little element is called indium, and though you may have never heard of it, your daily life depends on it. Where did it come from? And why does it behave so strangely compared to other metals? Welcome to Cube Chemistry, where we will discuss all the elements of the periodic table and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel for next week, as we will be discussing another experiment again. Now, at first glance, indium looks like a piece of frozen silver. Smooth, bright and metallic. Freshly cut, it shines a silvery white luster, almost like polished chrome. It's unusually soft for a metal. Press your fingernail into it and it leaves a mark. Bend a bar of indium and it gives a faint crackling sound, known as the tin cry. Unlike iron and copper, indium doesn't tarnish quickly. It keeps the quiet silvery glow for a long time. And that brings us to the segment, Can You Lick It? Now, while it may look harmless, indium is not something you'd ever want to try to taste. It isn't chocolate, and it isn't necessarily safe. The pure metal isn't as dangerously toxic as mercury or lead, as we can see in the periodic licking table, but indium and its compounds can damage your body if ingested. Even touching it so much without protection isn't a good idea, so licking it, as our table suggests, I do not think is a good idea. So let's see if indium is radioactive. And for that, we have a bonus segment that is provided by our sponsor of today, RadiaCode. We can immediately tell it is not radioactive. Now, RadiaCode is the next generation smart radiation detector, dosimeter and spectrometer. If you want to learn more, go to radiacode.com. Now, unlike simple Geiger counters, like the one I showed in previous videos, RadiaCode gives you the power to explore and visualize radiation in real time. Whether you're a scientist, an adventurer, a geologist, or just curious about the unseen world around you, RadiaCode makes discovery possible. Here, I've placed several radioactive cubes: uranium, thorium, radon, plutonium, of which we've all made videos. You can see we got much quicker results. Let's use RadiaCode to demonstrate its incredible sensitivity. With advanced scintillation sensors, RadiaCode is up to 20 times more sensitive than standard Geiger counters. It simultaneously displays dose rate and count rate with customizable smart alerts. Now, when connected to this free mobile app, RadiaCode transforms into a pocket-sized spectrum visualizer, allowing you to see and interpret isotope visualization, such as uranium-238, radium-226, or potassium-40. RadiaCode also records GPS tracks and creates radiation maps you can share with the world through Radiaverse, an open geosocial platform built for explorers and enthusiasts. With long battery life, Bluetooth and USB connectivity, and models ranging from the compact RC102 to the ultra-sensitive RC110 that we have here, RadiaCode is built for discovery anytime, anywhere. Start exploring the unseen. Visit radiacode.com, get your RadiaCode today, and join me in discovering the invisible world around us. Now, the story of how indium was discovered is a fascinating tale of color and chemistry. The element was discovered in the year 1863 by two German chemists, Ferdinand Reich and Hieronymus Theodor Richter. At the same time, scientists were actively searching for new elements, and a powerful new tool had just emerged: spectroscopy. By heating samples and looking at the light they emit through a prism or a spectroscope, scientists could identify elements by the unique colored lines they produce in the spectrum, like each element's fingerprint of light. Reich and Richter were examining minerals from ore in the mountains in Saxony, specifically a zinc ore called sphalerite, zinc sulfide, which we've discussed last week in our zinc episode. They suspected that their ore might contain a recently discovered element named thallium. Thallium had been discovered a couple of years earlier by its bright green spectral line, so the German duo set up a spectroscope to look for thallium's green signature in their zinc ore sample. There was a slight catch. Ferdinand Reich was colorblind, which meant that he could not easily distinguish certain colors in the spectroscope. He relied on his colleague Richter to be his eyes for the experiment. Now, when they analyzed the sample, they were in for a big surprise. Instead of seeing a green line of thallium, Richter observed a brilliant blue-violet line shining back at them, a color no known element was known to emit. They had stumbled upon something completely new. This vivid indigo blue spectral line revealed the existence of an unknown element in the ore. Reich and Richter had discovered indium. They chose the name indium because of that distinctive indigo line. The name comes from the Latin word indicum, meaning indigo, which itself means Indian, referring to the indigo dye originally imported from India. In essence, indium is named after a color, the deep blue indigo color it shows in the spectroscope. After the initial discovery, the two scientists worked to isolate the pure metal. By 1864, Richter managed to obtain a small amount of indium metal. A few years later, in 1867, they presented a sizable indium ingot, about half a kilogram, at the World's Fair in Paris, proving that this was not just a laboratory curiosity, but a real metal that could be extracted. Interestingly, a dispute arose between Reich and Richter, with Richter later claiming he deserved sole credit for discovering indium. Such squabbles were not uncommon in the history of chemistry, as pride and fame were on the line for discovering new elements. Regardless, both men's names are remembered for indium's discovery. It's worth noting that indium was one of the last new elements discovered in the mid-19th century using spectroscopy. By the time indium was discovered, chemists already knew about cadmium and other elements in zinc ores. But indium had gone unnoticed until the advent of spectroscopy revealed its indigo signal. So, indium discovered in 1863 was part of a wave of using new technology to find what had been invisible to early chemists. Indium is a chemical element that belongs to the same family as aluminum and gallium. At first glance, it looks like a typical metal, shiny and silvery white. But it's far from ordinary. Indium is extremely soft and malleable. Now, in fact, like mentioned in the intro, you can cut indium with a knife with almost no effort, a bit like slicing a piece of firm cheese or a bar of chocolate. If you rub a piece of indium metal on a paper, it will leave a mark like a pencil. That's how soft it is. It's also very ductile, meaning that you can bend or twist it easily. Now, unfortunately, I don't have a piece of indium yet, but when you bend it, it makes a strange high-pitched crying sound that isn't a creature inside the metal, it's actually the sound of the metal's crystal structure crackling slightly. A phenomenon indium shares with its cousin, tin, known as the tin cry. Another remarkable thing about indium is its melting point. Pure indium metal melts at only about 156 degrees Celsius or 313 degrees Fahrenheit. Now that is hot, but for a metal it's quite low. Most familiar metal melts at about several hundred or thousand degrees. Lead, for example, melts at about 327 degrees Celsius and silver at 961 degrees Celsius. Indium's melting point is closer to the temperature of baking cookies in an oven. Now, while you can't melt indium in the palm of your hand, unlike gallium, a related metal that melts at near body temperature, if you want to see an episode about that, click on this video next, a gentle heat source is enough to turn solid indium into a liquid. In the world of metals, indium really does melt like chocolate. In other words, it liquefies with relatively little heat. Now, this low melting trait makes indium very useful in special low temperature alloys and devices, as we will see later. And even in solid form, indium can feel a bit like a soft confection because of how easily it can be deformed or scratched. Now, chemically, indium is classified as a post-transition metal. It sits in the periodic tables, group 13, nestled between gallium, like mentioned before, above it, and thallium below it. Its properties are in between those two neighbors. Gallium has an even lower melting point, about 30 degrees Celsius, which is why gallium can melt on a warm day in your hand. Whereas thallium has a higher melting point, around 304 degrees Celsius, and is notoriously toxic. Indium's toxicity is much lower than thallium's. In fact, indium is not known to have any biological role in our bodies, and pure indium metal is considered only mildly toxic, though indium's compounds or dust can be harmful if inhaled or ingested over time. This low melting point means indium is termed as fusible metal. It can be fused, melted, and cast with ease. Now, interestingly, indium doesn't boil until a very high temperature, over 2000 degrees Celsius, so it has a huge gap between melting and boiling. When indium is liquid, it also has an unusual ability to wet surfaces like glass. Now, what does that mean? If you have ever seen water spread out on a clean glass surface, liquid indium can do something similar. It doesn't form droplets as easily as mercury does. It tends to stick and coat surfaces. This property of wetting glass and other materials make indium useful as a sealing material in certain engineering situations. For example, sealing vacuum systems with indium wire. In terms of other physical traits, indium is fairly dense, but not extremely so. It's about 7.3 times as dense as water, 7.3 grams per cubic centimeters, which means it's heavier than common metals like aluminum, but lighter than metals like silver or gold. Now, a chunk of indium in your hand would feel hefty for its size, but not ridiculously heavy. Indium is also non-magnetic, as most metals like copper, gold, etc. are. And it conducts electricity and heat. Though not as impressively as copper, still its thermal and electricity conductivity are decent for a metal. One more exotic fact. When you get indium extremely cold, just a few degrees above absolute zero, around minus 270 degrees Celsius or so, it becomes a superconductor. That means that it can conduct electricity with zero resistance. This phenomenon, however, is common to many metals at cryogenic temperatures and requires lab conditions to observe, so it's more of a scientific curiosity than a practical property for everyday life. Chemically, indium behaves in ways we might expect for a metal, but with a few interesting twists. In chemical compounds, indium usually shows up with a +3 oxidation state, meaning it tends to give away 3 electrons and form triply charged ions, indium 3+ in compounds. For example, indium oxide is In2O3, which implies indium is +3 since oxygen is -2. Now, indium chloride is InCl3, etc. Now, this is similar to aluminum, which is also mostly +3 in compounds. However, indium can also exist in a +1 oxidation state in some compounds like indium chloride, for instance. The +1 state is less common, but it exists because indium's 2 inner electrons, the 5s electrons, technically speaking, sometimes prefer to stay put rather than bound, a tendency known in heavier elements as the inert pair effect. This effect is even stronger in indium's heavier cousin, thallium, which prefers +1 in many compounds. In simpler terms, indium is usually trivalent, forming compounds like InCl3, but can occasionally behave as monovalent, like indium chloride, showing a bit of chemical flexibility. Now, when it comes to reactivity, indium is not a wildly reactive metal. It is stable in air at room temperature, and indium metal piece will slowly develop a very thin layer of oxide on its surface, but it won't tarnish quickly or corrode like iron would. Indium does not react with water, so you can drop it in water and it won't fizz or dissolve. Only strong acid will dissolve indium metal. For instance, indium will slowly dissolve in strong nitric acid, forming indium nitrate and nitrogen monoxide gas. If you heat indium in pure oxygen, it will eventually oxidize to indium oxide, a yellow or clear compound. Indium also reacts readily with the halogen elements like chlorine, bromine, iodine to form indium 3 halides. Now, one fun chemical interaction is with sulfur. If you heat indium with sulfur, they'll react to form indium sulfide, which is a compound that was historically used as a yellow-orange pigment in glass and paints. So indium can form colorful compounds. Now, perhaps even more useful is indium's love for forming alloys with other metals. Indium can mix alloy with many metals, often lowering the melting point of a mixture dramatically. A striking example, if you take indium and its neighbor gallium and simply press them together, they will start to dissolve into each other and form a liquid alloy. There is an alloy, 75% gallium and 25% indium by weight, that stays liquid down to 16 degrees Celsius or 61 degrees Fahrenheit. That is almost room temperature. Add a bit of tin to that mix, creating an alloy of roughly 68% gallium, 22% indium, and 10% tin, and you get the famous room temperature liquid alloy called gallium, a replacement for mercury in thermometers and other devices. So, indium, when combined with the right partners, helps create some very low melting, even liquid metal alloys. Indium doesn't form certain types of compounds that might expect. For instance, there's no stable indium carbide or indium silicide in the way that there are for some other metals. And indium hydride is so unstable, it basically falls apart immediately at normal conditions. Now, this just highlights that indium's chemistry is somewhat limited to those +3 and +1 states with certain partners. In biological terms, indium doesn't react in a way that integrates into living processes. It's not used by any known enzymes or life functions in plants or animals. Our bodies don't need indium, unlike, say, iron or zinc, which are essential nutrients. Now, if indium compounds get into the human body, they tend to be absorbed well orally. But inhaling indium dust or fumes, like indium tin oxide fumes in industrial settings, can be toxic, especially to the lungs. So while metallic indium is relatively benign to handle with usual hygiene, indium chemicals should be handled with care like most heavy metals. Now, indium is a rare element in the Earth's crust. It's not fantastically rare like some platinum group metals, but it's pretty scarce. To put a number on it, indium is estimated to be about 50 parts per billion in the crust, and that means for every billion atoms in the crust, there may be about 50 of those that are indium. This concentration is comparable to elements like silver or mercury, so in the grand scheme, there isn't a lot of indium just laying around. Now, because of this low abundance, indium doesn't usually accumulate in rich ores by itself. In fact, only a handful of indium-containing minerals are known, and they are quite uncommon. One example is a mineral called rockosite, copper indium sulfide, and there are a few others, but you'd be hard-pressed to find a chunk of rock made of mainly indium minerals. There are no indium mines where miners dig out pure indium ore. Instead, indium is typically found as a trace ingredient in other metal ores. The most important source of indium is zinc ore, specifically the mineral sphalerite, which we also discussed in last week's episode of zinc. In many deposits of zinc, a tiny amount of indium substitutes for zinc within the mineral structure. Think of it like a few indium atoms sneaking into a lattice of mostly zinc and sulfur. These amounts can be just tens of parts per million, but when you're processing huge volumes of zinc ore, those little bits can add up pretty much. Indium can also be found in small quantities in some copper and lead ores for similar reasons. Indium can also sometimes be replaced in copper minerals like chalcopyrite or accompany tin in cassiterite deposits, but zinc ores remain the primary source. Interestingly, indium very rarely occurs in its native metallic form in nature. It's just too reactive and too scarce to accumulate that way. There have been a few very rare reports of native indium metal in some ore veins, usually mixed with other metals, but those are mineralogical curiosities. Indium production is a great example of how nothing in mining goes to waste. As we noted, indium is mostly obtained as a byproduct of refining other metals, especially zinc. Here is a simplified version of how that works. Now, this process looks rather similar to the process that we've discussed in the zinc episode and the cadmium episode, so we will rush through it. When zinc ore sphalerite is mined, it's concentrated and then usually roasted to convert into zinc oxide. The zinc oxide is then leached with acid and eventually electrolyzed to produce pure zinc metal. Now, throughout these steps, the indium that was in the ore doesn't follow the zinc into the final product. Instead, it tends to collect in the residue or in certain intermediate solutions. The residues, which might have weird and wonderful names like zinc smelting dust or crud, are what indium's producers are interested in. Now, from those residues, indium can be extracted by chemical processes. Often, the residues are treated with strong acids or alkaline solutions to dissolve indium. Because the concentration of indium is still relatively low, chemists use precipitations or solvent extraction techniques to separate indium from the other metals in the solution. The indium is then eventually concentrated and purified. One of the final steps is usually electrolysis, similar to how aluminum is made, where indium is plated out of the solution onto a cathode as indium metal. Because indium is tied to zinc and to a lesser extent copper production, the availability of indium each year depends on how much those base metals are being produced. If tomorrow we stopped all zinc mining, indium supply would dry up, even if there is indium still in the ground, because no one mines zinc just to get indium. It wouldn't be economical to mine such a low indium concentrations alone. Historically, the amounts of indium produced were very small for a long time. In the early 20th century, only tiny amounts were extracted. In fact, Germany had the only major source for decades, since they had a zinc industry that extracted indium. It wasn't until around World War II that indium production ramped up significantly, for reasons we will discuss in the applications section. In recent times, as the demand for indium skyrocketed due to electronics, production has also increased. Today, around a few hundred tons of indium are produced globally each year. To give an idea, on the order of 700 tons per year in the late 2010s, though this can fluctuate. China is currently the leading producer of indium, thanks to its large zinc smelting industry, followed by countries like South Korea, Japan, Canada, which also have major zinc refineries that recover indium. One famous indium producing facility is the zinc refinery in Trail, Canada, which has historically been one of the single largest sources of indium in the West. Even with increased production, indium is still considered a critical or strategic metal. There have been concerns about its supply because our modern gadgets use so much of it, but the good news is that the analysis show that we are not about to run out of indium imminently. As long as we keep mining zinc, we can probably extract a lot more indium than we currently do. If needed, there's indium in many ore deposits that we haven't bothered to extract yet, because demand has been met by easier resources. However, recycling is also important. A lot of indium is locked up in discarded flat screen displays and electronics. Efforts are underway to recycle indium from e-waste to ensure a steady supply and reduce the need for fresh mining. One of the most important uses of indium today is in your screens. Yes, the very screen you might be watching or holding. Most modern touchscreens, flat panel TVs, computer monitors, and smartphone displays contain a component called indium tin oxide. Indium tin oxide is a mixture of indium oxide and tin oxide that has a really useful property. It's transparent like glass, but also electrically conductive like a metal. This combination is rare. Normally conductors like metals are opaque. You can't see through a copper wire. And transparent materials like glass are insulators. ITO gives us the best of both worlds. In an LCD or an OLED display, ITO is used as a transparent electrode. A very thin film of ITO is deposited onto the glass of the screen in patterns. These act as the circuits that control each pixel. But because the layers are transparent, they don't block the light coming out of the screen. If you have a smartphone, there's probably a layer of ITO just under the glass that is helping detect your touch by carrying electrical signals across the screen, and another in the display itself to lighten up the pixels. Without indium tin oxide, we wouldn't have the kind of bright, responsive touchscreens and high-resolution displays we enjoy today. We'd likely be stuck with much less efficient or more bulky alternatives. Another big category of indium's application is in making special alloys and solders. Remember indium's knack for lowering melting points when mixed with other metals? This is exploited to create fusible alloys that melt at a relatively low temperatures. These have a variety of uses. For instance, automatic fire sprinkler systems sometimes have a fusible alloy as the trigger. The alloy holds a plug in place, and if a fire heats the room, the alloy designed to melt at, let's say, 70 degrees Celsius or 158 degrees Fahrenheit will liquefy and then release the plug, allowing water to flow. Some of these alloys contain indium combined with bismuth, tin, lead, or cadmium to get just the right melting point. Indium is also used in certain types of solder, the metal glue used to join components in electronics. Standard solder is usually tin-lead mixture, but for some applications you want a solder that melts at an even lower temperature or has special other properties like remaining soft or being non-toxic. Alloys with indium with tin or indium with bismuth and other metals can create solder that melts at a much lower temperature than ordinary solder. These are useful if you need to solder something to a delicate component that can't take much heat, or if you're soldering on heat-sensitive substrates like glass. Now, indium's ability to bond and seal is used in vacuum systems too. Indium wire can be laid into a groove and used as a seal gasket between two metal or glass surfaces. When you tighten the seal, the indium deforms and fills any microscopic gaps, creating an airtight or vacuum-tight seal. This is commonly done in ultra-high vacuum chambers or certain cryogenic apparatus when rubber gaskets would fail. Historically, one of indium's first big uses, back in World War II, was a coating for bearings. Engineers found that adding a thin layer of indium on engine bearings, particularly in aircraft engines, helped the bearings last longer. The indium coating was an anti-corrosive and also helped hold lubricating oils. This was a big deal for wartime aircraft, which needed every reliability edge they could get. Although this is no longer a primary use, bearings and oil formulations have evolved. It was a significant chapter in indium's history. Here are some other applications that we will not dig into much further. It's also used in nuclear reactors. Indium is good at capturing neutrons. It is used in neutron detection. Related to the above, indium foil or wire can be used to detect neutrons in scientific experiments. It's also used in mirrors and coatings. Indium can be used to make certain kinds of mirrors. For example, indium metal can be evaporated onto a surface to create a reflective coating. Thermal interface is also a use. Indium's softness and high thermal conductivity makes it useful as a thermal interface material in some electronics. And of course, like many elements in medical imaging, in nuclear medicine, a radioisotope of indium, indium-111, is used as a tracer. Doctors can attach this radioactive indium isotope to molecules that seek out certain tissues or infections in the body. Indium may not have the fame of gold or the everyday ubiquity of iron, but this unassuming metal is a true hidden hero of the modern world. It's the metal that melts like chocolate, soft, fusible, and delightfully different from the hard, refractory metals we usually think of. That very softness and low melting point have been turned from curiosity into an asset, allowing engineers to create alloys that protect us from fire and solder our most delicate electronics. Meanwhile, indium transparent conductivity oxide has become the window. In a world of technology and color, indium truly shines in its own subtle way. Whether melting with ease, sighing when bent, or lighting up our screens, indium proves that sometimes the smallest player can have the biggest impact. It's a reminder of the wonders hidden in the periodic table, and who knows what other ordinary elements might hold secrets just as sweet as indium's chocolate melting charm. Now we would like to thank the members that support our channel. Thanks for doing this, we really appreciate you. Now if you think we missed anything, tell us in the comments, and if you want to know more about another element that melts extremely quickly, make sure to watch this episode about gallium next.